Okay, so there's some chalk in here, I think. Okay. Okay, so this is talking about valuation theory and its interaction with commutative algebra. So this is a subject, at least Zariski was very interested in this, if not before, where you have a valuation whose ring is, valuation rings are generally non-Noetherian, and dominating a Noetherian ring and seeing what you can say about it. And it's very interesting. So also that where this one application of this is to local uniformization. So I'm going to start talking about things that appear to be just sort of purely this kind of valuation theory / commutative algebra, and I'll be able to give at least one application to local uniformization or local resolution of singularities. Okay, so the setup is I'll take V to be a valuation of a field K, and let me get this here. Just a second. I should have done this right in the beginning. Okay. 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 So it looks like we're 331. Okay, and associated to this, there's a value group, which I'll write like this. Okay, and there's also a valuation ring with the maximal ideal. One thing to keep in mind is that this ring is a Noetherian ring if and only if the value group is the integers. And there's lots of examples. For instance, the value group could be the rational numbers, which is not, so the valuation ring is not Noetherian. Okay, so then tying in with Noetherian commutative algebra, I'll take A to be a Noetherian local ring. And with the same quotient field K, and which is dominated by the valuation. So what that means is that, I guess I should say a domain, otherwise it won't have a quotient field. And that means that basically I'll represent this by a picture diagram like this, an arrow. And I also convey in this that not only is there an inclusion here, but the maximal ideal contracts to the maximal ideal here. That's the relation of dominance. Okay, so there's one construction in here which really goes back to Zariski, where you have an ideal, and then you can take X to be the blowup of I to the spectrum of A. And this has the property that there's a unique local ring of X, which is dominated by the valuation. Local ring A1 of X, which is dominated by the valuation. So one has a diagram, vertical arrows, which we will write like that. So this gives a method, as Zariski realized, to talk about birational questions in commutative algebra, questions which depend upon quotient field, and you're allowed to blow up some, maybe improve things. But then there's lots and lots of points when you blow up, and then you're not really in commutative algebra quite anymore. But the valuation picks out a specific local ring, a unique local ring. Okay, and another comment about this is that you always have that this is a union of these rings which are essentially of finite type over the base ring A. So there's a directed system of these rings, or I'll call them AI. I call that to be a birational extension. Okay, so birational extension means that it's a local ring of a blow-up. So in other words, it's just a ring which is a finite type, essentially a finite type, a localization of a finite type A algebra, and which is the same quotient field. Okay, so the valuations, as I mentioned, was a vehicle for studying things, problems, local birational questions such as local uniformization. Okay, now there's a kind of ring associated with this, which was introduced by Tessier in his quest for local uniformization, which he calls the associated graded ring along the valuation. The associated graded ring along valuation. Maybe I should clear this here. Which you write like this, nu A, and this is the direct sum, like this. I'll tell what these things are. The sum is over gamma inside the value group, and this is defined by the elements F and A, which have value bigger than or equal to gamma. And the other one with the plus, it's going to be strictly bigger than gamma. Okay, P gamma plus A is equal to F in A such that the value of F is strictly bigger than gamma. Okay, so this is almost never a Noetherian ring. In fact, even if the group is the integers, it's very often not Noetherian. Okay, so now what we want to study is how this thing here behaves when you take a birational extension. So this can be used to study problems in ramification and also problems in local uniformization. So the situation is I take a finite field extension, and I take an extension of nu to L. Okay, so that's a valuation of L which restricts to nu 1k. An extension always exists, and there's only finitely many of them. That's part of the classical theory. And there's a couple of very classical invariants which are true for general valuations. There's the reduced ramification index, which is the index of value groups. That's always finite, even though these groups themselves are not. And there's also the residue degree, which is the index of the residue fields, which is also always finite. Even though these groups themselves, these fields themselves can be quite big. Okay, now these are the ones which are, the E and F are the ones that are maybe familiar from algebraic number theory, but there's another one that's not so familiar, which is called the defect. And I will not quite define it, but I'll tell you something about it. And this is called the defect. And it was introduced by Ostrowski in the 30s. And this is always a power of the residue characteristic of the valuation ring. And it has the property that you can always reduce to the case by some trickery where you're looking at an extension where there's a unique extension of the valuation. And in that case, there's a formula for it by Ostrowski, which is that if omega is the unique extension of nu, then one has the formula that the index of fields is equal to E, F, and then this defect delta. Okay, so in this defect is basically where problems come in, that things tend to work very well using these valuation theoretic techniques until you get defect, and then there's lots of problems. The thing which should be kept in mind is that this will be 1 unless a characteristic is positive. So the defect does not occur in characteristic 0. This is called Ostrowski's lemma. And the importance of this, I think, was actually pointed out fairly recently, importance in local uniformization by Kuhlmann. Even though it was known in the 30s. Okay, so our interest is in Noetherian commutative algebra. So we look at this situation. We will suppose that A and B are Noetherian local domains with the quotient fields, respective quotient fields K and L. And we're assumed that it's dominated, B dominates A, and the valuation ring of omega dominates B. This forces the valuation ring of nu to dominate A. Okay, so this we'll assume they're of the Noetherian end of the same dimension. Okay, so that gives us an inclusion of these associated graded rings, which are always domains. And one can, in fact, compute the index of the quotient fields. That should be a B there, of these things. And this is equal to E times F. Okay, well, somehow you're looking locally and doing this, so maybe it's not a great surprise that you lose this information about any problems that's happening from non-uniqueness of extensions. But it's kind of interesting that this defect, it disappears. You don't see it here. But in fact, it doesn't really disappear because it'll show up, as we'll see in a few minutes, in very subtle behavior in this extension here. In fact, the defect only causes trouble. It causes lots and lots of trouble, and we'll see something about that. Okay, so in fact, I will raise a question about this, which will indicate what I'm talking about. Okay, so this is a question which is, are the following and in fact, I could change this question a little bit without assuming this. But I'm going to assume that A and B are excellent in here. This is an assumption which does not bother algebraic geometers, although I know many commutative algebraists are very, very troubled by putting such a strong restriction on rings. So you could, in fact, get rid of this if you wanted to. And there exists a diagram like this. Like this, where always this is domination, where here the vertical arrows are birational. Okay, well, remember that means that they have the same quotient field, and A1 is obtained by A by it's essentially a finite type. It's a localization of a finite type extension. Same thing with B1. And also, this is where I'm using excellent. I'm making them normal. Well, somehow that just came out of the way I was looking at this. And the critical condition is that the extension of associated graded rings is finite. In other words, Ker omega nu 1 is a finitely generated Ker nu A1 module. Okay, so remember that these rings themselves are almost never finitely generated in any sense. They're not Noetherian. But still, one can hopefully get this condition. Well, what is this equivalent to? That the defect is equal to 1. In other words, there is no defect. So in other words, if you can achieve by some blowing up a situation where it's finitely generated extension, that it should exactly mean that there's no defect. And in fact, it's not difficult to construct examples where there is no defect, but if you look at your initial extension A to B, it's not a finitely generated extension. So you do have to blow up. So this is truly a birational condition. Okay, so a theorem, a positive theorem, is that the question has a positive answer if K is a characteristic zero algebraic function field. Okay, and I'm also, when I say that, I mean that there's some ground field, not necessarily algebraically closed for the function field, and A itself is a finite and affine ring over that. It's a finite type extension over the ground field and then localized. Same thing with B. So the theorem is really completely true in this case, and in fact in that case it's just there's no equivalence business because 2 never happens. Okay, because remember this is a power of P where P is the characteristic of the residue field of the valuation. So in this equi-characteristic 0, this implies that the defect is equal to 1. There's no defect. Okay, so somehow one might be wondering, well, why would I think the defect have anything to do with this? This is a much more general theorem. And what I will give you a theorem which I think indicates this might be true. There's basically a difficulty in that in general it's very hard to compute these rings. After all, they're not finitely generated. And even showing when somehow it's a little easier to compute extensions, and we'll get back to that. But in general, that's also a difficult problem. And there is one case, well, for one-dimensional rings, it can be done. But for the case for the interesting non-Noetherian valuations, there's really one case where it's completely understood how to compute these associated graded rings. And that's for two-dimensional regular local rings. It also happens to be that resolution of singularities is known to be true for two-dimensional regular local rings. So one has a lot of techniques. Okay, but this next theorem, which I'm going to state, is the way it is because of this issue that I can compute, and in fact I will say with difficulty one can do the calculations of the theorem for two-dimensional regular local rings. And that's the category which it's stated in. So this is the next theorem. Okay, so let's suppose that, again, A and B are two-dimensional excellent local domains. I guess I need of the same dimension. Then I will say that the defect is equal to 1. There's no defect if and only if there exists a diagram like this. A to B, A1, B1 into R omega, where here we have again that the A to A1, the vertical arrows are birational. And in order for it be possible for me to calculate things, I'm going to assume that A and B1 are regular. Okay, that's a category I understand. And having the situation that we have the finite generation. Now in this case, I'm saying finite generation as an algebra. And I'll make a comment after I've written that Y algebra here and Y module there. Ger omega B1 is a finitely generated Ger nu A1 algebra. Okay, so the problem is, stuck as I am in my category of regular local rings, that in general it's not possible to achieve an extension of regular local rings along the valuation where both A1 and B1 are finite or quasi-finite. or in the old language that B1 lies over A1. In fact, Abjanker himself gave an example showing that this is not possible for certain types of valuations in dimension 2. So to get this to be a finite module, you can only do that if B1 is quasi-finite over A1. Okay, so if you do some more blowing up, this is the best you can hope for to be a finitely generated algebra. Okay, but you see that while it's a little different, I think this does suggest that maybe that question has a positive answer, or maybe it's the right question to ask. That you see very strongly here this lack of finite generation in the extension, and it being stable under blowing up is equivalent to this lack of defect. Okay, so in other words, you have a lot of trouble if there are defects, at least if you're interested in studying such examples. Okay. Okay, so I'm going to say a few words about how you can compute extensions of associated graded rings along a valuation. In fact, I don't know if I have time to get to it, but one of the things that, if I do have time, is a method which allows you to do a lot more calculation, which is of many extensions, which is quite recent. But this is an old method of MacLaine, and I want to mention that we'll see how far I can go talking about this. Anyway, I'll at least be able to talk about my local uniformization theorem, and we'll tie it in with this. So what MacLaine showed, this was in 1936. There's a series of nice papers he has, which is says that if you have a discrete valuation nu, discrete in his case means the group is the integers, then there exists an algorithm, which I will call MacLaine's algorithm, to compute the extensions of nu to a valuation which is necessarily discrete, W of the polynomial ring K adjoin X, or a valuation omega of a finite extension K of X of F of X, where he has a very beautiful algorithm to do this. And in this case, where it's where you mod out by some unitary polynomial, in this case that this is in fact a pseudo valuation W of K of X. So in other words, there's a value of F becomes infinity, something which is bigger than any element in here, that they're equivalent formulations. Okay, and I don't really have time. I would like to actually go through this whole statement, but I don't have time, his whole wonderful algorithm, but I don't quite have time for it. So I'll say a few words about what the shape of it looks like. Okay, so you start out in his algorithm. It iterates. V naught's your initial algorithm. And what he shows is that there exists an augmented sequence of valuations of V1, V2, Vk. Maybe you stop after a finite k, or maybe you keep on going and construct a countable sequence such that either your extended valuation is Vk for some finite k, or it's a limit valuation of these guys. One of these two will get to it. Now, this is where I wish I had more time to talk about it, but I'll say something, that each vk is determined by what MacLaine calls a key polynomial phi of k, phi sub k, which is contained in k of x, and over bk minus 1. Okay, and somehow if you construct these things, you get a nice algorithm for computing the value for anything in k of x. These things have success, they're all unitary of increasing degree, and using Euclid's algorithm, you expand an arbitrary element in here in terms of these guys, and you can read off, excuse me, what the valuation is from that. Okay, so now, we're interested in the non-discrete case, and basically you can start with MacLane's algorithm, and if you're lucky actually, and maybe we'll have time to see that in some cases this very same algorithm will work for a general valuation, but not always. And the problem that can happen is that what can happen is that you can kind of get stuck if the value group isn't the integers, and somehow you can have you can take x and you subtract elements in k, and you can get bigger and bigger things which don't go off to infinity. There'll be maybe like the value group could be a subgroup of the reals, and maybe you'll get closer and closer to pi, but never quite get there. Something like that can happen. And if that happens, then you're stuck there, that you'll just accumulate up at that point and you'll never get finished. You have to end up where the value of these things get bigger, eventually go off to infinity. The last one has, the last key polynomial will be f, which is value is infinity. So in fact, the k recently, or more recently anyway, compared to 1936, he did it in 2007. He generalized this whole theory to general valuations, and basically that's what he had to do, was to deal with this case where you have a kind of an accumulation. This extended to MacLane's algorithm to general valuations. Okay, and this is by constructing limit key, so-called limit key polynomials, and this will be somewhat cryptic, but this is a really beautiful part of the theory, giving jumps, what he calls jumps. And the jump measures the defect. This is what's really interesting about it. Measures defect and the failure of uniqueness of extensions. But the significant thing is the defect. So if you have an accumulation point where you say you're heading to pi or something like that, you never quite get there, then what you have to do is somehow, all right, you realize that you've got this infinite family of things, and then you have to jump over it somehow. And if that happens, then you know you have to have defect in the extension. Okay, so now I can talk about a theorem on local uniformizations. Okay, so this is an application to local uniformization, or local resolution of singularities. So in fact, Zariski in the 30s, it was the same time actually that MacLaine was doing this. So these guys didn't seem to talk with each other. It was kind of interesting. They seemed to have no idea they were doing the same thing. But in 38, that Zariski used valuation theory to prove that you can resolve surface singularities. And the way he did this was he proved it first this local uniformization, that if you take a valuation, then you can, by blowing up enough, you can make resolve a singularity along the valuation. And the way he came to this was he had this classical algorithm which due to Beppo-Levy. And what it is you take a surface singularity, you normalize it. Okay, so a normal surface will have only finitely many singular points. You blow them up, then you normalize again. Okay, well, what the claim is that this will eventually terminate, that you, after a finite number of steps. And the way the proof starts is you think, okay, let's suppose it doesn't. Then you'll have an infinite sequence of points, one mapping down to the other, where you always have a singular point. Well, if you take all of these normal rings and if you take their union over all of them, that will construct a valuation ring in the way I talked about in the first few minutes. And that's where the problem comes in, is that very unlikely it's going to be a nice valuation. You should presume it's some awful thing with maybe the rational numbers as a value group or something like that. So that was what got Zariski interested in this problem. And eventually, about 10 years later, or in 1944, it was published, less than that, he proved local uniformization and characteristic 0 for any valuation. And one of the parts of the proof is he has a reduction to rank 1 valuations. So a rank 1 valuation is when a number theorists say valuation, either they believe it's only the integers, or they believe there's some kind of a metric which is giving it that the value group's contained in the real numbers. So that's the condition. That's what rank 1 means, is that you can embed there's an order preserving embedding of the value group in the reals. Okay, so let me say this theorem. This is with myself and Hussein Mortada. So let's suppose that nu has rank 1. And A is a regular local ring. This is the classic condition. And also one assumes that you have some kind of induction statement on dimension, something called embedded local uniformization holds in A. So in other words, if you have say some f in A, you can blow up in A, blow up regular primes in A to make f, the strict transform of f be in fact, make f itself to be a unit times the system of parameters. Okay, and that statement will follow if you can prove improve local uniformization, or at least in a strong enough form in that dimension. So this is a kind of proper induction statement. Okay. Then here is the critical assumption. Okay, so here we have A into k of x mod f of x. This is the assumption that we're having in here, and we're assuming that this should have been a of x mod f of x, and we're assuming that the defect is 1. Okay, so then reduction of multiplicity of f is possible. So in other words, by blowing up, the strict transform of f has lower multiplicity. So if one could always do this, then one eventually get the multiplicity down to 1, which means it's non-singular, so you've achieved local uniformization. So this is the basic induction step in almost all proofs of resolution of singularities where they're successful. Okay, so see how I'm doing here. Okay, I'm doing a little better than I thought. Okay, so maybe I should say something. Reduction to multiplicity 1, that implies the local uniformization. And as I mentioned, that this should imply at least the form which I'm doing it here. If you can do it without the defect restriction, that would also imply this embedded local uniformization condition without too much trouble. Okay, so I'll say one more comment about how it ties in with MacLane's algorithm. So if you perform MacLane's algorithm, you start performing this here, and what happens is you always start out taking phi 1 is equal to x. Okay, and then what you check and you ask yourself, well, what is the order of the value of phi 1 relative to the group, the original value group of nu? And if it's inside the value group of nu, then you have to make a translation. Okay, and if it's not, then you go to you take an appropriate power of x to put its value inside the value group, and then your new, say, n1, so then your phi 2 would be phi 1 to the n1 minus something, and so on. So the degree would have gone up, gone from 1 to n1. And if the algorithm is successful and computes the valuation, then the last step was you build up the degrees until the last guy is going to be your original guy f. Okay, but where you're really getting into trouble is if you get into the situation where you have a limit point, a finite limit point, then you could just keep spinning around and you never finish. Okay, and that's the worst case situation where you have a jump right in the beginning where the MacLane's algorithm will always have degree 1. So in fact, that if in MacLane's algorithm the degree is, even if you don't get the whole valuation, if the degree of some phi I is bigger than 1, then you win. Obtain reduction of multiplicity. Okay, so this is in fact really the obstruction, this kind of crazy phenomena, this defect. This is the obstruction to local uniformization in characteristic P. Okay, so I'll say a few words about the proof. Okay, so our essential assumption is the lack of defect. And what this implies is that if you take the set of W of x minus k, so in other words, you look at all values of x minus some element in k, and you see what this looks like, that this condition here implies that you have no jump from MacLane's or Vaquet's algorithm, and this therefore has to have a largest element, gamma, which is, we can write this as for some a in the field K. Okay, or there's another possibility, or there is no bound in the value group, And this case is not difficult. I won't talk about it, but this isn't fairly easy case that you can in fact resolve the singularity completely in this case. Okay, so we'll just ignore it. We'll look at this case. Okay, now necessarily the value of this A has to be positive because the value of the X is positive. So that means that since it's in the value, then it's in the valuation ring of nu. So after some birational extension of A, you can get that little a inside that. So I guess I called it Blowup. I guess I'd already used that word before. Along nu to get this A in A1 and A1 regular. That's where we're using the embedded localization. So that we can preserve this, we can preserve that condition. Okay, okay, and then you make a change of variable. Variables changing x to x minus a to get that the omega of x itself has that maximal value gamma. Okay, now since this is maximal, that this is maximal, that implies that that gamma cannot be in the value group of nu. Because if it were, then you just find something that in here in k, which has that value, and then you can subtract that from x and get a higher value. So that's the this is the key thing which makes it work. And it's kind of a long technical calculation, which I won't tell you about because we don't have time. I'll call it technical, but actually I think it's a nice calculation. I like algebraic calculations. So then in fact you can take a birational extension of A1 followed by another kind of birational transformation in all variables. So I'll call it a Cremona transformation, as Zariski did, involving x. And then to get a reduction of multiplicity. Okay, so I'm not really going through how this occurs, but somehow having this fact that the value of x is not in that group is just what you need to, after doing some calculations, get the be sure that the multiplicity drops. Now, this was inspired by Zariski's characteristic zero proof, and it does not work. Zariski's algorithm completely fails in characteristic P. And in fact, what he does is his algorithm in characteristic zero, he does not have to blow up. In fact, the algorithm is such that it finds on its own the element A. So what it does is it tries x. If you get a reduction of multiplicity, that's good. Then you're happy. If you don't, however, the algorithm shows that there actually has to be something, some element A or some element in k which when you subtract it from x you have a higher value. And also because you're never leaving the original ring, which is Noetherian, you can only make this change of variables finitely many times. because you know there's some upper bound for it. So he actually realizes this inside the ring itself. But you see, if you're in characteristic P and you just start running his algorithm, well, you see that doesn't work. So you know, but you do realize that if you blow up some, then you could make a change of variables. And there's no reason, if you look at this, you'd like to think that it'll terminate eventually, but it's not clear. And in fact, what this shows right here is very clearly exactly what happens. It's exactly a matter of this defect. That if there is a defect, then you can never make the algorithm work. It doesn't matter how much you blow up. But if there is no defect, then you're guaranteed that after some finite blow up, you'll get what you want. Okay, so I go till 4:30. Is that correct? Okay, so I think I just have time to mention this one statement. So. If I had mentioned that somehow only being able to do these calculations for these groups in dimension 2, and obviously I had to be able to do something in general for this case to get the characteristic 0 case, but in general it's rather difficult. But this is something recent, where, in fact, in the characteristic 0 case, one of the steps is to resolve the singularity. So everything's regular in it. We're in characteristic 0, we can resolve singularities. But only a few examples were known of actual singularities, things which are not regular, where you can compute anything about the value groups. And this is something that's very recently with Hussein Mortada and Bernard Tessier, where here that there's no rank assumptions, has arbitrary rank. And we take f in A of x, when we assume that P does not divide the degree of f, where P is the characteristic of A. In fact, there's an assumption here where I have a field K in A, and A mod is equal to the residue field is algebraically closed. Actually, none of this is really necessary, but algebraic geometers like assumptions like that, and the statement in the theorem looks a lot nicer if I'm working over an algebraically closed field. But I think there's a very similar statement to this, which is true with absolutely no assumption on A at all. I don't even need A to be excellent. Omega is the unique extension of nu to k of x mod f of x. Then there exists a realization of MacLane's algorithm which produces a finite number of key polynomials. So it terminates after a finite number of steps. Polynomials phi 1 out to phi k, which actually all live inside A of x. You don't have to take a birational extension. such that well, first off, the pseudo valuation is actually VK, and the associated graded ring of this thing is the extension of the associated graded ring of X by the algebra generated by K things, which are in fact the classes of these guys, modulo an ideal I with the very simple form. This has this nice form because this assumption the field is algebraically closed. Otherwise it would be, it'd still be finitely generated, but it would be much more complicated. Okay, so it has this very nice expression like this. C sub i's bars are the class of some element C, I, and A. Okay, so it's a very simple kind of binomials which generate this. And in particular, this is a finitely generated and presented GR nu A module. Okay, so just say a few words about how this ties in with defect. Did I say it was a unique extension? Yes. So remember in the beginning of the talk I gave Ostrowski's lemma, telling you that in this case, since it's a unique extension, the degree is going to be the degree of the field extension, namely the degree of f, is going to be equal to EF times the defect, which is a power of p. Well, this tells us that p does not divide the order of the field extension, so you cannot have any defect. So this works this way because there's no defect. And in fact, you can say that if you're in a general field extension, finite field extension, and you're looking at something like f and a of x, that in general you can ask the question, when does there exist a birational extension a to a1 where there's a realization of MacLane's algorithm which gives the valuation, and that happens if and only if there's no defect. Okay, so I'll stop here.
Any questions?
The associated graded ring that is given here, does it turn out to be usual commutative algebra associated graded ring you said it's not even Noetherian in many cases.
Most of the time, yeah.
Yeah. So in two-dimensional local ring case, at least, does it turn out to be the usual associated?
Well, it can. If you, for instance, if you're in a two-dimensional regular local ring, there's the M-adic valuation. Okay. So if you take this ring for the M-adic valuation, that's exactly the usual associated graded ring. And something I didn't mention was that even though this was actually defined and in this very nice, pretty looking modern language and notation and so on by Tessier, but it turned out actually Bernard himself found out sometime afterwards that MacLaine had actually already defined this in his 1936 paper. So it seems to be natural for studying valuations. Also, Bernard had mentioned that actually this ring appeared actually in some appendices he wrote to some lectures that Zariski gave in Paris for curve singularities, where the thing's always finitely generated in that case. And there are valuations and discrete valuations.
Thank you.
Thank you.